All right, today, guys, we're going to look a little more at complex numbers, looking at our imaginary number I. We're going to look at some patterns that I has, and then start looking at some operations. So our learning target for today is I can perform operations with complex numbers. Not the kind like the game when you were little, not the Grey's Anatomy kind of operations. We're talking about like the order of operations, add, subtract, multiply, divide. Okay, and actually for this first part, we're going to look at exponents. If we take our value of I and raise it to a power. All right, so we know that I is equal to the square root of -1. That's what we defined yesterday. So what we can do now, what if we took I and squared it? All right, and again, thinking about what it means if I square a square root, right? So I is the square root of -1. If I square a square root, that basically cancels the square root out. So the square root of -1 times itself, if I square that, is just -1. All right, so the value of I squared is -1. Now, if I look at, if I take that, so I know that I squared is -1. If I want to do I to the third, let me make sure you can see that. Ooh, sorry. Let's see. There we go. All right, so I to the third would be the -1 we've already got, and I would multiply it by another I. So -1 times I, again, I've already got I squared, I'm multiplying by another one, is just -I. All right, so say I take that -I and I multiply it by another I to get to I to the fourth, right? So that would be -I, because I to the third is -I, times another I, which is -I squared, since it's I times itself, and we already determined that I squared is -1. So if I've got -I squared, that's -1, which is a positive 1. All right, now here's the interesting thing, right? If I were to then take 1 and multiply it by another I to get to I to the fifth, 1 times I would be I. If I multiplied I by another I to get to I to the sixth, I'd have I squared, which is -1. And it would keep repeating itself in this cycle, in this pattern, okay? So basically what's happening is there is a pattern of how I works, right? And it goes I, let me write it up here, we can see it. So it goes I, -1, -I, and then 1. Those are the 4 terms in the pattern. So I raised to any power can only be one of these 4 possible things. Okay, so now if it's just 1 through 4, that's pretty easy. We can tell. But what if it's a higher power, like 1 to the 57 or something? How would we know what that is? I mean, I to the 57. So then we can use, there's only 4 terms in the pattern, right? So what we can do is divide the given exponent by 4, all right? So if we divide by 4, let's use my example of I to the 57, all right? 57 divided by 4, whoops, make sure you can see that, there we go. 57 divided by 4 is what? Well, let's see. 57 divided by 4 is 14.25, all right? So what in the world does that mean? Well, think about quarters, right? Think about in terms of a dollar, right? 0.25 would be 25 cents. That would be 1 quarter. There's 4 quarters in a dollar. So there are 4 terms in our pattern, right? I, -1, -I, 1. So if it ends in 0.25, all right, that means the remainder is 1 and it's on the first term of the pattern. Okay, so if I divide my exponent by 4 and the remainder, the decimal ends in 0.25, okay, then the term is gonna be I. So if the remainder is 2, so if I divided an exponent, let's see, like 50, well, let's just go up. The next one would be 58, right? So if I did 58 divided by 4, it's 14.5, okay? So if the decimal ends in 0.5, that means we are on the second term. Again, if you think of quarters, 0.5 would be 50 cents. 50 cents is 2 quarters, my second term there. All right, if the remainder is 3 when I divide, then I'm on the third term, negative I, and you probably guessed that would end in 0.75 on the decimal. And then if the remainder is 0, so if it divides evenly and I get a whole number, then the answer is +1. That means it is on the fourth term in the pattern, which is the last term before it starts over again. All right, so let's look at a couple examples here. All right, here we have I to the 23. All right, I to the 23rd power right here. So I to the 23rd power, again, if I did 23 divided by 4, and I'm just kind of writing this to the side. So 23 divided by 4 is 5.75. 5.75. So we said that if it ends in a 0.75, that means it's on the third term in the pattern, which is negative I. Could also think about it, right? 0.75, 75 cents, 3/4. So I'm on the third term, which is negative I. All right, here I have I to the 300 power. So if I did 300 divided by 4, that's going to give me a whole number. I think it comes out to 75. Let's see. Yeah, 300 divided by 4 is 75. So that means that I got a whole number, not 0.75 like this one. I got an exact whole number. So when I get a whole number result by dividing my exponent by 4, that means we have a whole dollar. We're on the fourth term in the pattern, which is +1. All right, so that's all we're looking at here with these. So you've got the ones you could try. You're just going to divide by 4 and then follow this pattern right here based on what you know about the decimal it ends with and which term you're on in the pattern. Okay, so those are going to work out. I to the 64th is +1. I to the 101, I to the 101 power is I, just one I, and then I to the 442 ends in 0.5, so it's -1. All right, so there's our powers of I, looking at raising I to various powers. Okay, now I also follows the other properties of exponents. All right, we have several properties of exponents. This chart here in your notes reminds you of those. This is one we use a lot, the product rule, that if I'm multiplying two terms that have an exponent and they have the same base, so in this case A or I or whatever it is, then I add the exponents together. We use this one a lot as well, the power rule, a to the x raised to the y power, I multiply, that's a to the x times y. All right, and then there's some others here that are helpful to remember, but we're primarily going to focus on those rules right there, and then also this power of a product rule, which is just if there's more than one thing being raised to the same exponent, the exponent applies to both of those terms or all three of those terms if there's three of them. Okay, so let's look back at some of our examples here. All right, so we're using the exponent rules to simplify. All right, now numbers behave the way numbers always do. Okay, so if this dot means multiply. If I said, hey, what's 3 times 4? You would say 12. Every time. These numbers are not going to do anything different than what they normally do. So 3 times 4 is 12. I times I, that's using one of our exponent properties. I would add the exponents, that's I squared. So if this is equal to 12I squared, well, what value does I squared have? We just looked at that. I squared has a value of -1. So this is actually 12 times -1, which can be more simply written as -12. So that's the idea with these, is we kind of condense them down with just one single I term and one single number, and then write it as simple as possible. All right, so here I have I to the 3rd times I to the 7th times I to the 5th. So I'm multiplying 3 terms, same base. The rule is I'm adding my exponents. So 3 plus 7 is 10 plus 5 is 15. So this would be I to the 15th power. And then I need to simplify that. So we'll use the process we just learned. 15 divided by 4 is 3.75. Since it ends in 0.75, 75 cents. That'd be the third term in my pattern. And remember, it goes I, -1, -I, 1. So the third term is -I. All right, this next one here, I have 2i to the third, the quantity 2i to the third, raised to the third. So what's going on here? This is that power of a product rule I was telling you about. Everything in these parentheses is being raised to the third power. I like to draw a little marking to remind myself 2 is being cubed, and so is I to the third. So 2 cubed, and you could type that in the calculator if you need to. 2 cubed is going to be 8. 2 times 2 times 2. And then I to the third, I'm going to multiply those. 3 times 3 is 9. So that's I to the 9th. So then, again, use my same procedure to figure out the value of that. 9 divided by 4, 2.25. It ends in 0.25, right? 25 cents would be 1/4 the first term, which is I. All right, so I simplified 2 cubed into 8. I simplified I to the 9th into I. Now it's just 8 times I, which is just 8i. All right. So now the last example we're going to look at here, this has more parts to it. Okay, so I'm actually going to write this on a separate paper. All right, so we have 3i to the 5th times 4i to the 3rd. And notice that 4 and the I are both being raised to the third power. So times 4 to the 3rd, and then I to the 3rd. And then in my denominator, I have 8i squared. All right. So now what I'm going to do is see if I could simplify any of these numbers. So I could do 4 to the 3rd power is 64. And then what I'll actually do is, if this is 64, use a different color here. Since this is 64 and I have 64 in the numerator and 8 in the denominator, I'm going to reduce that. 64 divided by 8 would be 8/1. So now I have 3i to the 5th times 8i to the 3rd over just I squared, because I canceled the 8 out. All right, so now I multiply the numbers just like normal. 3 times 8 is 24. I'm going to add my exponents here, I to the 5th times I to the 3rd. 5 plus 3 is 8. 24i to the 8th. And then it's over I squared. So there's one last exponent property to look at, and that is the quotient rule. And I don't really like the way they've written it here. We more often would see it as, let me put it right here, a to the x over a to the y is equal to a to the x minus y. So when we're dividing exponent terms with the same base, we subtract the exponents. So let's look back at our example here. I to the 8th over I squared, I would subtract. 8 minus 2 is 6. So I have 24i to the 6th. What value does I to the 6th have? 6 divided by 4 would be 3/2, or 1.5. Okay, so that means it's 24 times -1. So -24. And that's about the worst they would get, where we had several different things to multiply out and simplify. But we end up here with just plain old -24. All right, so take some time to try the others, pause the video, and then when you're ready, you can check your work. Okay, and here's those last 4. So the final thing we're going to look at here is adding and subtracting complex numbers. So remember, those complex numbers are when we have a real and an imaginary part to our number. So we always want to write these in the final term a plus bi, where the real term is in the front and the imaginary term is in the back. So what we're going to do here, you're basically combining like terms. Just the I is going to act kind of like an X right now. So if I have 8 minus 3i, that's one complex number. All those parentheses mean is this is a single complex number plus a second complex number, 4 plus I. So what we do to get it in standard form, we write the sum of the real terms together. So 8 plus 4 is 12. And then we would put the sum of the imaginary terms together. Negative 3i plus 1i would be negative 2i. And that is in our standard a plus bi form that it needs to be in, so we don't do anything else. That's it for addition. It's very, very simple for addition, thankfully. Subtraction is a lot like the addition, except that we're subtracting the second complex number, which means the signs in that complex number change because we're taking them away. All right, so I like to rewrite all my terms. So I have 7 minus 4i and then minus 9 minus 6i, right? So I just took that negative on the second complex number and distributed it, basically. Now it's an addition problem. Identify the like terms and combine them. So the real terms are 7 and negative 9. 7 plus negative 9 would be negative 2. And then the imaginary terms, negative 4i and negative 6i, they have the same sign. They're both negative. So they combine to make negative 10i. And again, it's a plus bi. I have the real part, the imaginary part. I don't combine them any further. And that's it. All right. So you can knock out those last three, check your work, and you're all set. There's those three.